Good afternoon, everyone. I'm Arun Thakur, the MDO at IEEE SIGST, and I'm thrilled to welcome you to day three of the fourth edition of Epsilon, Synergy of Realities. It has been an incredible journey so far, and we are so glad you are here with us as we conclude the Women in Engineering track. I'm excited to be the part of this final day of our symposium. Over the past 2 days, we have dived deep into the topics like neurobites, the next wave in computing, and building a simple spiking neural network. It has been a remarkable experience, and we are not done yet. Today, we are bringing it all together with an insightful panel discussion. As they say, the only limit to our realization of tomorrow is our doubts for today. So let us cast those doubts aside and embrace the limitless possibilities of neuromorphic computing. We have got an outstanding panel of experts who are about to lead us into the future of this exciting field. So without further ado, let us dive right into it. Please join me in welcoming our distinguished panelists who are here to share their knowledge, insights, and vision for the future of neuromorphic computing. Now, let's move on to the heart of today's session, the panel discussion. We are honored to have a distinguished group of experts who will lead us through an insightful exploration of the future of neuromorphic computing. I am thrilled to introduce our panelist and moderator for this session. First, let me introduce our moderator. We are honored to welcome Dr. Vijaya Patil, an expert in business analytics and data science. Dr. Patil serves as an assistant professor at Willinger Institute of Management and has over 15 years of teaching experience at SIGST Graduate School of Technology. She holds a PhD from IIM Bombay and an MSc in mathematics from Savitribai Phule University, graduating with distinctions. Her expertise includes predictive analytics, operation research, and statistical modeling. IEEE SIGST is delighted to welcome you, Dr. Vijay Patil, ma'am.
Thank you, Aryan.
And now, let us meet our esteemed panelists. First, we have Mrs. Hanga Katrina, a space engineer specializing in neuromorphic computing and space debris mitigation. Her expertise includes neuromorphic swarm intelligence for object classification in low Earth orbit, with experience from the European Space Operation Centers and Galileo's second generation satellites. She has also led a team in designing a space mining station for the International Space Challenges Singapore 2024 and is currently involved in a space startup focusing on small satellites. Let's give a hearty welcome to Ms. Hanga Katrina.
Okay, so hi everyone. Um,
I'm not sure what to say now. You really did an amazing introduction of myself. My connection is a bit lagging, so if you can repeat the question or the task what I should be talking about now, then I would really appreciate it.
Next, we have Dr. Sunny Baines, a distinguished scientist and journalist at University College London, UCL, where she teaches technical communications and journalism. With over 30 years of experience, Dr. Baines has written extensively on neuromorphic engineering, robotics, and machine cognition for renowned publications like The Economist and Wired. She also produces the Brains and Machines podcast with electronic engineering types and is authorizing a new book on neuromorphic research. IEEE SIGST is pleased to welcome Dr. Baines as she shares her insight with the fascinating world of neuromorphic research.
Good morning from Edinburgh.
Our third panelist is Mrs. Lana Usa, who completed her MSc in Electrical Engineering with a focus on microelectronics from Delft University of Technology in 2024. Her research on insects inspired intelligence for sensor computation integration, which led to innovative FPGA-based hardware solutions. Currently a trainee at European Space Agency (ESA) and the European Space Research and Technology Centre (ESTEC), Mrs. Usa was awarded the National North Atlantic Treaty Organization (NATO) Women and Girls in Science 2024 award for her work on AI-based cognitive warfare monitoring. IEEE SISGST is honored to welcome Mrs. Usa. Joining us as well, Mrs. Vidhi Vaghela is a tech enthusiast with a strong focus on data science, cybersecurity, AI, and machine learning. With a bachelor's in information technology and a master's in AI and machine learning, she is committed to advancing technology in a secure and innovative way. Vidhi also runs the blog Data Science Meets Cybersecurity, where she provides insights on complex technologies. IEEE SIGST warmly welcomes Mrs. Vidhi. Now it's my pleasure to hand over the stage to our esteemed moderator, Mrs. Vijaya Patil, for the panel discussion.
Thank you so much, Aryan, for the nice introduction for each and every panel of the panel discussion. Really, we have a great panelist over here for the future of neuromorphic computing. Now, so this is like as we gather here today, the computing world in verge of a paradigm shift, one that draws directly from the architecture of human brain. Neuromorphic computing is not just about faster processors, but fundamentally changing how machines think, process information, and make the decisions. Our panel today will unpack what makes this technology revolutionary and how it could redefine the future of artificial intelligence. So now to begin with, what inspired the development of neuromorphic computing and how does it mimic the structure and function of a human brain? So this is the first question I would like to pose in. So, if just a minute, I'll just pose this question in the box as well. So that first question. So to begin with, what inspired the development of neuromorphic computing and how does it mimic the structure and function of the human brain? So Leah and I have put the question in the chat box. So please, we can refer. So if Sunny could start with, hey Sunny, you're not audible. You're on mute. You're on mute. Uh, no, Sunny, we can't hear you. Okay, just hello.
Just my sound settings to see if they've
Yeah,
somehow changed. No, it should be on my AirPods. Here, let me try and put the input as my. Can you hear me now?
yeah, perfect, perfect, Sunny.
Okay. All right. So I had the honor to interview Carver Mead a couple of months ago. Carver Mead is the person who's commonly credited with being the founder of neuromorphic engineering. He's based in the States. He was working at Caltech when he did this. I have to say that he's not the only person who was involved with the founding of that field. There were people like Paul Mueller, who actually, I believe, did the first electronic brain model, which was a hearing model. But what Carver said to me when I was talking to him was, for him, the secret was parallelism. And even today, I would argue that parallelism is not entirely exploited. We have a kind of parallelism of cores, right? So we have lots of little chips that are running in parallel, but actually what's going on in each of those chips is serial, right? So you've got lots of serial um, machines running in parallel to create the AI that we know today. But his interest was in parallelism, and of course the retina has parallelism in it. And that was the way that, from his point of view, neuromorphic engineering started. It was taking this parallel computation that he wanted to do and working with his colleague Misha Mahawald, uh, which I hope you've all heard of, the Misha Mahawald Prize, which is awarded for work in neuromorphic engineering every year. She sadly passed away very young, I think in her 30s. But she was a really inspirational figure who built artificial retinas back in the 80s and early 90s. So you should look her up if you haven't heard of her. But I think that's what Carver Mead would say, is it was all about parallelism and being able to do lots of things at the same time, which the electronics can do. But because traditionally we've thought about von Neumann computing, we haven't pushed enough in that direction.
Vidhi, could you just go ahead? Vidhi?
Yeah, sure. On the same question, yeah. Am I
Yeah,
audible?
yeah. Hi. So
Yeah,
because see, we have a diverse audience over here. So let us start with the introduction of the what exactly and
yeah,
how it is different from the uh, traditional computing.
yeah, sure. Definitely, I'll start. So basically, putting it into the simple language, the basic term of the neuromorphic means brain-like structure and the function. So let's dive into the start of this neuromorphic computing. So like in 1890s, researchers started building the computers But meanwhile, while performing or operating the deep learning algorithms and all, they build, the computers' capabilities and the abilities were not enough. So they were trying to build computers that operate more like a brain to benefit from the brain's unique capabilities. This led to the birth of, we can say, the neuromorphic computing, where basically the systems are designed to imitate the way neurons imitate in our brains. So let's start, like, how does exactly the neuromorphic computing mimic the brain? So we have all heard about some terms like neurons and synapses, like the basic. So in neuromorphic systems, the artificial neurons and synapses are present, much like the biological counterparts in the brain. So similarly, neuromorphic hardware has interconnected circuits that mimic these interactions, enabling the system to process information in the diverse and maybe in the parallel manner. The second would be like the learning and the adaptation, if I put it into the simple language. So neuromorphic systems can learn from experience, how our human brain learns from experience, like from like how we age, we gain more experience, and the brain is uh, put under the experience to learn more and more. The same way, um, learning happens through the synaptic plasticity, where connections between the neurons are strengthened and maybe weakened by the means of experiences. And the last one would be the energy efficiency. One of the, like, if I say, the one of the brain's most remarkable feature would be the energy efficiency. Even when a human brain performs a complicated task or complex task, it requires a huge like thinking power. The more energy goes for the human, the same way the brain uses around 20 watts of power if we calculate. And it's same as the fun fact, if I speak, it's the same as the light bulb. Also, the neuromorphic systems aims to achieve the similar efficiency by reducing the energy required for data processing, which again helps us to counter the normal computing which we do. And neuromorphic systems are much faster than the normal computings, which is particularly important when we talk about the autonomous systems like robots, drones, or anything that we use in the large scale AI systems. So this was the part I would like to share. So that's it from me.
Yeah, great, Vidhi. Actually, great, Vidhi. You have explained it in a nutshell. Now we'd go ahead with Hanga and I mean check her perspective about this. Yeah.
Okay, so I think you already covered the historical phase of neuromorphic computing, and I'm more into the software part. So I started to get deeper into this field from this perspective, and from what I gathered, yeah, neuromorphic computing is a type of computing that mimics the way how the human brain works. So traditional computing processes, you know, so they process information in a linear and sequential manner. But in neuromorphic computing, you do this in parallel. So you can adapt to new information in real time more efficiently. And that's what really got my attention. From what I see, so these systems use these so-called spiking neural networks on the software level, at least, to mimic this way how the neurons communicate through various electrical impulses, and this allows for basically an efficient and adaptive processing. And I think the important thing is that these neurons do not transmit the information at each cycle that we are getting used to, only once a so-called threshold is reached, and that enables them to create a more efficient system, basically. That's how I see it.
Okay, Liana. Okay, fine. So we'll go to the so this is what is the difference between the traditional computing and the uh, neuromorphic computing, because uh, the this is like a brains, as Vidhi rightly said, as Hanga rightly said, that this is nothing but a neurons what we are having in our brain, and that is what is so giving the computer the brain like structure is in a nutshell we can say, and we can go ahead as a the homomorphic computing. Now moving ahead with the next question is, so why neuromorphic computing seen as a promising solution for artificial intelligence and machine learning? So why this is look like a promising uh, this one? Can anybody what would like to go ahead? Yeah, please. Yeah, Sunny, please go ahead. So
So
now
if we
I'm
just,
keeping my mic on, and
thank you.
yeah, yeah, please
Okay,
proceed.
so my take on it is that there are several places where neuromorphic engineering can be really helpful. One of these is in robotic applications where the amount of computing power that you would want to put inside an embodied robot is so great that you would not expect to be able to do it using conventional digital approaches. Also, even if you could, the amount of power being expended would be too high for any kind of batteries that you could imagine being able to create for these robots, and there would be too much heat produced, right? So there are all sorts of issues of size, weight, and power in robotics. But likewise, in lots of other situations. So I wouldn't want to step on Dr. Katrina's work, but of course she does stuff in space. So anywhere where you've got things that are far away that can't be powered easily, anything small. So also in the Netherlands, I don't know if you work with him, but Guido de Kroon does some neuromorphic stuff with flying robots. There's also biomedical stuff. So if you want a prosthetic that can really respond
Yeah,
in some kind of intelligent way, then and feed information into the brain, that's a really good application where neuromorphic, where again the power is an issue, the size is an issue, the weight is an issue. If you talk to people who wear prosthetics, they'll always tell you that weight is a really serious problem if the limb that they're strapping on is too heavy. And other kind of biomedical applications like sensors inside your body, and also actuators inside your body, things that are stimulating,
yeah.
whether it's a nerve or plugging straight into the brain. Lastly, I would say, and I think this may be on the list for later though, but in artificial intelligence in general, like the kind of way we think of artificial intelligence now, which is really just generative AI and asking, answering queries and that kind of stuff, which is what most people think about. Actually, the amount of power that these server farms burn up, both in the training and in the recall, the inference mode of doing AI today, is so vast that it's really problematic. So people are really having to work hard to try and find the energy to power these things. And neuromorphic approaches, if you embed them into even existing kind of infrastructure, or in existing approaches to doing things, if you merge the two, then that could be very powerful. And less energy, more computational power.
Correct, correct, absolutely. So here, Henga, any say on this particular? Henga, are you able to listen to me? Or there is a
Yeah,
lag,
yeah,
I guess.
yeah.
Yeah,
I just missed if it was me or not. Um, Yeah, I think we. So first of all, if we think of a new technology, um, for so what I do is always check if it's applicable to certain fields, especially on the field that I'm interested in, and if it's really needed there or not. So this is, I think, a huge thing that we need to consider first before we actually introduce something into any kind of system, because there will have some uh, there will be some impacts on the industry itself as well. And as you know, I'm working in the space sector, and I started to do this research on space debris mitigation. But I really needed to focus on certain sub niches or subfields where I can apply this specifically, because for space debris, you can use it for tracking, you can use it for detection, you can use it for classification. You have to decide this. Um, and once you decided, you can go for the why and the how. So, for example, in scope of space debris, I think this would be a huge benefit for the industry, because at the current state, we don't really use artificial intelligence at all in the space industry. Yes, you have some researches, but not in the actual production, or just very few ones. So we have to evolve on these fields, and I think neuromorphic computing can enhance our technologies. For example, if you just think of small satellites where you have really you have to be really energy efficient, and you have to use you have limited power that you can operate on in space. You really need to grab any kind of opportunities that you have currently that you can implement in these fields. And I think this is, from the space perspective, neuromorphic computing will be really interesting and is really important to just take into consideration due to this energy efficiency manner, the event-based processing. You know, you have to get data near real time, if not real time, if you want to detect an object, because that can lead to severe collisions and other, so it raises other risks if you don't act up on these problems. So I see this more an enabler for the space industry.
Great, great. Actually, I'll definitely would like to come back to you with the space industry and a few good applications related to the this computing. Vidhi, are you there, Vidhi? We would like to see your perspective on this particular. Vidhi? Okay, I think Vidhi has lost connection. Liana? Liana? Sunny, you are writing a book on this particular topic. So, could you just focus few light on some software or hardware or some upgradation in the current computing or traditional computing, which is required for this computing?
So I should say that my background, my first degree was in physics. So when
Mm-hmm.
so I'm kind of the opposite to Hanga in that she comes from a software background. So whereas I come from a physical sciences background, and what that means is when I think about neuromorphic engineering, I'm thinking about the energy flow, the electrons moving through systems. That's what actually, and also the photons, because you can do neuromorphic engineering with photonics, or at least people are trying to. It's much more remote than doing it electronically. But again, creating spiking neurons and things using optoelectronic backbones. But the thing that I think has the most potential is that, first of all, you can be using analog circuits instead of digital circuits.
Yeah,
This gives you a
correct.
big advantage in terms of power efficiency, which I talked about earlier. It can also be a lot faster. So I don't know whether our listeners have heard of the event camera, but one of the really neat things about that is that an event camera essentially, instead of having frames, right, which every 30th of a second are being captured and then sent to some signal processor to be dealt with an event camera, the pixels are live all the time, but they only send information at the point where something changes. So if they've just got a constant illumination, they're not sending any information. What that is a sort of an automatic image compression, which is really nice because it means you don't have to have quite the same level of infrastructure in order to communicate that data, that information coming off. It's very low power. And because these pixels are ready at any split second to send some data if something changes, they can change in a thousandth of a second. So you can have
Mm-hmm.
so you have these cameras that are a combination of a frame camera and an event camera. So what you can do is you can take the frame and update it based on the events, which are very highly time sensitive, and get completely blur-free images. So Toby Delbrook at the INI Zurich, at the Institute of Neuroinformatics in Zurich, and also Prophecy, which is a company based in Paris. They've both done stuff like this, but where they show you they with one of these cameras, very cheap camera, incidentally, you can show
Yeah,
the picture of a tennis ball in the fastest part of it's being served, and you
speed.
can
Huh.
actually see the ball, which would be impossible using conventional cameras. So there are all sorts of interesting
Mm-hmm.
things that way. But to me, it's all about dynamics. To me, it's about the information is not being blocked by these clock signals, right? That the image can flow, and that gives you a dynamics that a physicist really likes.
Great, great. So this is what the computing is advancement of computing is happening. Now, for the Liana and Vidhi, I would like to repeat the question. In between, people, both of you have lost the correction, so we have just gone through a little bit of to Sunny to address her few contents from the book. We will definitely try to take out more for her in a upcoming this one. So now we are having this question that why neuromorphic computing seen as a promising solution for the future of artificial intelligence and machine learning. Liana,
Hi, yes, can you hear me? I
hi.
managed to join after 30
Yeah, yeah.
minutes.
Perfect,
Perfect.
perfect. Yeah,
Yes, great. So when I just tuned in, maybe just a little bit of background of myself. I actually worked at Prophecy. I did my internship there, so I can tell you about. Um, yes, I'm still on. Good. So it's definitely true that with neuromorphic there is a great potential in AI and machine learning, future AI
machine.
and machine learning, of course. And now what's interesting, what I would like to always emphasize with neuromorphic computing and engineering side. So you have approach and the top-down approach. So with the bottom-up approach, you would look into sensors such as the event-based cameras, event-based sensors that have this approach of mimicking the way that sensory systems, for example, humans are capturing their environment. And then the top-down approach would be to look into how you can reuse that intelligence for efficient and effective computing, which is definitely helpful in both AI and ML approach. And so why neuromorphic computing is promising for the future is exactly because of that. You have this two-sided solution actually, in which you can use the sensory way as well as the intelligence of biological systems to kind of
Systems.
mix, to get the best of both worlds and to improve performance, to improve energy consumption, and also scale. So the size of things that we definitely currently just really want to scale down, but have the huge computing power with the increasing demand of data and increasing demand of well, neural networks, for example. So that's why I would say it's a promising solution for the future.
Yeah, great. Vidhi?
Yes, ma'am. I think the most of
Yeah,
the points are covered by the panelists. We can move on.
okay, free. Great, great, great. So the moving, so definitely computing has the upper hand on this particular and would be helpful in this. So, but what are the common challenges that beginners face when entering the field of neuromorphic computing, and how can they overcome these hurdles? So, what are the some common challenges that beginners face when entering in the field of neuromorphic computing, and how can they overcome these hurdles? Anybody from the panelists can take up the question.
Okay, then maybe I can start.
Well, I can.
I would
Well,
only focus on the software side of you, but I started my research somewhere in January or in February, so I'm also pretty new in this field, and I'm sharing the struggles of a beginner. So that's what I gathered.
Great.
And for my challenges, the first of all, the interdisciplinary knowledge that it is, let's say, not required, but it's really good to have. So you not necessarily need to know every single field of neuromorphic computing that it combines, but having a clear picture in your head or in your mind really can help you define your subfield to, or where you want to take your put your focus on. The second thing that I saw and I experienced was the steep learning curve, because neuromorphic computing involves really complex and just fundamentally different concepts than, for example, traditional AI methodology. So you have to really be patient and persistent and stay curious. So I would say if you start with the small steps, you can keep yourself motivated. But don't expect to be an expert on the field from one day to another. It's a slow process, but you will get there. And the third thing, which is challenging, I think, is the frameworks or the tools and the set of rules and standards, because it's still a new field and it's still evolving. So these frameworks and these standards are very much limited. So standards would help you guide through, for example, an implementation process or just setting up some rules that you can follow. And in this particular field, I haven't found that many. So I feel the lack of them would be another kind of challenge for the beginners.
Okay. So that means you are, yeah, please, Sunny, please go ahead.
So all I wanted to say is that in the book, we decided not even
Hmm.
to, or the book isn't finished yet, so we could still change our minds. But at this point, my temptation is not even to really get into tools because I think they're at too early a stage, and I think they're going to really evolve over the next few years. And so for people who are out there, you just have to use whatever is appropriate. I mean, one of the problems we have is that each of the different chips, so whether it's the spec chip that's produced by, I always get their name wrong, SynSense, or the WiE chips, they all have different things that you need to program them with, which is really frustrating for a lot of people. And those are going to change. It would be great if they would standardize in the next few years. I don't know that it's going to be that quick, though. And some of the ones that are more Intel's uh, um, tool, my understanding is it's it's intended to be very general, but it's very hard to use at the moment. So it can potentially do a lot of things with a lot of different kinds of chips. But at the moment, my understanding is it's not that easy to use. So that's just in the nature of being at the forefront of a technology that's evolving. And for those of us who are in our 50s instead of in our 20s or 30s, you get used to that, right? When you start off, there are lots of programming languages floating around, or there are lots of different standards for this and that. And eventually, as the technology matures, it settles out. And actually, what you'll find is your adaptability, your ability to go from tool to tool, will be a kind of resilience for you in your career in the long run. That although it will be a huge pain and a huge waste of your time, or at least it'll feel like that as you're going through it, in the longer term, I think it will pay off in that you'll be able to sort of see something and know how to use it quite quickly once you've been around the block of a few of these.
Great. So collaboration is the key over here while working in the neuromorphic computing. Yeah, Liana?
Let's see. Hi. Okay, so I had to
Yeah.
reconnect again. Just so I think when I started neuromorphic computing, I actually started from a neuroscientific approach. So I was really looking into how did the sensor, does the sensory system of an insect look like, which was part of my master's thesis actually. And
Hmm.
soon I also found out that there was very little documentation on how to actually put it into a programming code and then run it on hardware. And for example,
Hmm.
I tried to use the WiE one, and what Dr. Sunny mentioned is, for example, the WiE chip, WiE 2, they have a specific microcode. So all the neurons that you, for example, the neurons that you want to use, the typical ones, they're already in there. But the ones that I wanted to use, they were not in there. So you have to find your way around it to make it work, which is challenging, perhaps annoying, but it also stimulates, you know, the whole journey towards the development of the network that you need for a specific application. And you will, in your way, even though it's not already there, in your way, you will be able to contribute to the future of neuromorphic computing. So just in short, to really explain it, because I do have to leave within 5 minutes. The current challenges, well, actually, right now there are a few uh, Git Git GitHub GitHub repos that you can use to
Repository.
start building your simple neural network. Yes, exactly. You can start you can start by actually look at them, and some are actually quite well documented. And that's what I would tell myself 2 years ago. Maybe start with something more simple, like trying to understand spiking neural network and the different learning rules that you have, because I did it quite in a harsh way where I wanted to just rebuild a sensory system without actually knowing what was already there. Again, now after 2-3 years, documentation has improved. There are GitHub repositories with nice documentation. So just have a look, literally just browse it, and you will find very interesting things on the web.
Great, great. Yeah, please.
I'd just like to put in a word for Neuropack. So if you go into, let me get the URL. So it's neuropac.info. We have a whole load of neuromorphic news, sometimes jobs. We don't get lots of jobs, but we do get a few. So, postdocs and things that are coming up. But also, most importantly, in the context of what Brianna just said, resources and tools. So when things come up and we hear about them, we post them onto that site. So this is funded by the NSF in the UK.
Okay, so this
I
is
also want to
other than
in
the
the US. In the US. Sorry, sorry. I'm in the UK. The NSF is in the US. I beg your pardon.
yeah, Liana, you were saying something.
also just quickly give a shout out to I want to quickly give a shout to a very nice neuromorphic computing framework where you can have the standard plasticity rules, but also work around it by creating your own code in Python. It's called Brian 2 simulator, the Brian 2 simulator. And they're currently doing improvements as well to enlarge their offer in the way like the neuron types and the plasticity rules, and it's a very user friendly framework to start just creating your own neural networks. I just wanted to give you that one.
Yeah, Vidhi.
Actually, I have one interesting point to add in here. For all
Please,
the ones
please.
who are just like the beginners or starting in the neuromorphic computing, as I have also started like 6 months back, and I was very confused like where to start, what to learn. So my suggestion would be just to start with the like simple AI concepts, like learning the libraries and frameworks, like which includes the TensorFlow or PyTorch. And there is one amazing software known as the Neuron by, I guess, the Yale University, which one can take up the courses and get started into the like something building like one neuron or one spiking neural networks or something. Yeah. So that was the point I wanted to add.
Okay. So this is actually our panelists are such a diverse because Sunny has already having the experience of working with the already in a collaborative. Hinga, Liana, and Vidhi, they are just started with the neurocomputing. So maximum we are following it. We are like getting the gist because our audience is the youngest audience. They are just going ahead and starting with the neurocomputing, this neuromorphic computing. So definitely they'll be getting a different idea about it. So let me just pose the next question on you all. That is the what are the most promising architectures for neuromorphic computers do they face in terms of the flexibility, uh, recognition, and performance? I'll put the question. What are the most promising architectures for the neuromorphic computing, and what challenges do they face in terms of flexibility and performance? even reconfigurability?
One of them, well, there are two ways that I can answer this question. If we're talking about neuromorphic architecture, I would,
I
as
think
a hardware engineer,
just one
I would.
just one Liana, somebody's mic is on. I think we are getting some voice. So just Liana is speaking, so rest of us will just keep it on mute. Go ahead, Liana.
Should I continue? So, yeah, what I was saying is that being a hardware engineer, when we talk about neuromorphic architectures, I would approach it from the hardware side, obviously. And currently, there are many hardware or neuromorphic hardware, such as the WiE, and there's BrainChip, but there are also more developer-friendly architectures which would use. Can you still hear me? Mm,
You're audible, Liana. Go ahead. Liana, you're audible. Just please go ahead.
Okay, yes, okay. My connection is acting weird. So did you hear the last part that you can also have more
Yes,
FP?
if you are if you are having a connection problem, you can just switch off your video and just you can talk. So you will get a better connectivity. Switch off the video and then you talk.
Yes, I tried that. Oh, my phone is acting.
Okay, somebody else can take up the question till Liana will come back. Yeah, please go ahead. Sunny, go ahead.
I just wanted to say that, thank you. I just wanted to say that neuromorphic engineering perhaps will always have a little bit of a challenge in terms of flexibility, in the sense that what's beautiful about neuromorphic circuits is that if they're done well, they're exactly what you need to do the job, a little bit like an ASIC, right? They haven't got, ideally, they won't have a whole lot of fat in them. They won't have a lot of overcapacity, because that's why you want them in the first place, is to be a lean, efficient, whether that's power efficiency, high power in terms of computational power, solution to a problem. But what that means is that they're going to be quite tightly defined in terms of the problem that you're trying to solve for whatever application that is. So my sense of it is, at least in the short term, we will not be using any kind of like generic substrate for doing a lot of tasks. So I think where in industry, where the action is going to be is creating neural networks that are designed for a particular task. Of course, if you've got these big cloud computing applications, like the big Spinnaker system that's just been launched a few months ago, or Deep South is coming on stream. We haven't mentioned Deep South yet. That is Andrei Van Schaik and his colleagues down at the University of Western Sydney are building a huge FPGA-based neuromorphic simulator. So it's a simulator. It's not actually neuromorphic, right? In the sense that the circuits are not neuromorphic that it's using. But the idea is to show, to give a platform for you to experiment with all sorts of different kinds of neural models and that kind of thing. So I think for simulation, there's all sorts of things you can use. Spinnaker too. a Spinnaker as well, I would say, is probably more of a simulator than a genuinely neuromorphic proposition. But they're valuable. But I'm not sure that that's where neuromorphic is going to end up. I think it's going to end up being very, very specific chips, at least in the short term. And then we've got this issue of sparsity, right? So one of the things that's potentially really nice about neuromorphic systems is because they're only encoding exactly what they need to, right? Because they're more efficient, they don't have like loads and loads of interconnections that aren't required. They're only using the interconnections they need. And if you can then take that approach and apply it to some of the existing technologies like GPUs, and move them more in that direction. I know people have been doing that, creating networks where you set things to zero. If they've got a low weight, for instance, on an interconnection, you can just kind of take a whole load of stuff out. And if you can then, put some of these things into hardware, then you get all sorts of interesting things. Now, I should say again, I'm not an engineer, right? I'm a scientist. My first degree is in physics. I'm a journalist. I know a lot about neuromorphic engineering. I don't have to build anything, right? So take the things I say with a pinch of salt. But I think that's where the sweet spot's going to be for neuromorphic engineering. It's not going to be big mainframes. It's going to be little chips that do something incredibly well and with incredibly low power.
Could
Yeah,
I
so,
maybe now add reconnect?
Yeah. Yes, Liana?
Oh, perfect, perfect. I really liked what Dr. Sani mentioned about that neuromorphic will be more like purpose built, so for specific applications. Now, for example, in April 2024 this year, BrainSkill has a second BrainSkill S2. That's what it's called. It's a second version of the previous BrainSkill, and it's a neuromorphic chip which is running at, I think, around 1,000 times the real biological speed. So that's also quite interesting to mention with, if we talk about actually mimicking, learning natural systems, it can actually take up to days. Because, for example, we as humans, we might need more than just a day to learn. But what is interesting about these accelerating neuromorphic chips is that they want to basically double, and in this case, 1,000 times, being 1,000 times faster than humans to process information. And that's where I also think the opportunity lies for future neuromorphic architecture is to look into these neuromorphic chips to process. To look into the chips that will accelerate this processing of information. So that would be more on the hardware side. And I think we're still in the question of what are the most promising neuromorphic architectures. So that would be something to look out for, this BrainSkill chip or something similar like. But I also think at the same time, developments in neuromorphic engineering can be quite expensive. That's why we still don't have customer ready chips. But at the same time, we do have a whole community with open source codes of actually looking into the neural networks that we can optimize before running it on a neuromorphic chip, for example. And this is also quite promising because now we are, for example, using more sparsity rules. We have different types of neurons. We have different ways of hyper optimization and optimization of parameters. It's also very important to already have an efficient neural network before putting it into a hardware. So both things can be something to look forward to.
Yes, correct. Actually, this is what is because you, Liana and Hinga, you are already working in this. Now, I think we will move ahead with the question and answer session. So, Somebody's mic is disturbing, I guess. We'll have to just take care of that. So, first question from the audience has popped up over here. I'll just copy this question and put it in our chat so that every panelist can see that particular question very well and just check that. I'll repeat it for you, for the audience as well as the panelists. Could neuromorphic computing contribute to significant breakthroughs in BMIS?
I don't know. I'm going to admit that I don't know what BMIS is in this context. BMI is body
Mass
index,
index.
body whatever index. So as far as I know, so could you tell us, whoever asked the question?
I think it's the brain-machine interface.
Yeah,
No?
brain machine interface.
Okay.
So I can answer this a little. Yes, I think it can contribute to brain-machine interfaces, and people are already doing it. I will not mention the name of the company owned by a billionaire who I don't like, who's sort of famous for doing that, but there are a lot of people working in this general area. One of my favorite systems that I've written about in the last few years was actually not plugging directly into the brain, because I think there are a lot of ethical issues related to plugging into the brain when you don't know what you're doing. But with a prosthetic device where they were using stimulation to go through the nerves. And of course, the nerves do go into the brain. I mean, the nerves are part of the brain, right? The nervous system of the body is part of the brain, really. So they were going through the skin into the nerves, but using a neuromorphic pattern, if you like, spiking pattern to reach the brain. And that meant that the control of the prosthetic was able to be done by the person's visual system, and then they were able to control and feel what was going on in the prosthetic. So there's some really interesting stuff going on in this area. I'm very excited about it. My colleague at Johns Hopkins University, Johns Hopkins is known for its his hospital, right, more than it is even for its university, which is a great university. And so you can imagine they're doing a lot of really interesting biomedical applications there. And so, yeah, I think it can help.
Yeah, Henga, you wanted to take this question, or we'll move to the next one?
No, we can move.
Yeah,
I think
yeah,
that's pretty nicely covered.
nicely covered, right? Fine. So next question is, what are the potential risks of neuromorphic systems in the terms of their impact on the job displacement?
Can I answer this question, or is
Yeah, please,
anybody?
please. Yeah, please go ahead.
Okay, so from what I see, or from what I understand, is there are two scenarios. One is that neuromorphic computing can create new opportunities in various fields.
Mhm.
And I'm getting back right now to the space industry again, because that's where I have more insights. But we don't have that many positions for AI in this particular field. And once we implement these techniques, we will surely need the workforce to cover this. And yes, on the other hand, it can displace some positions, but I'd rather see this as a shift of position. And as we still need a good workforce for just basically different tasks. So, and since it's a new territory, we have the opportunity and we have the option to think forward and to provide certain trainings and prepare these trainings for people who would be displaced, to make people more qualified for these positions rather just letting them leave the company. So yeah, there is the risk of displacement, but if you are willing to contribute, to something new, I think you can have the opportunity to shift your interest and field to keep the position.
Yeah, so I'll be moving ahead to the next one. Next is, what role could neuromorphic systems play in advancing personalized medicine and precision health? In advancing personalized medicine and precision health. Yeah, please. Yeah, Sunny, go
So
ahead.
from my point of view, one of there's a lot that can go on in this area. So one of the things, not with neuromorphic technology, with conventional technology that people are already doing, is creating like pills that can wait until the correct environment in the gut. So you swallow the pill, and then some sensor will sense when the right chemical is there, or the right enzymes, or whatever it is, and then can release their medicine. So there are all sorts of situations like that. Where it can help. So I think neuromorphic also, there are, you can imagine things on your skin that are measuring whether it's your temperature or changes in the skin, or actually, when I was at the University of California at San Diego for the NICE conference earlier this year, they're working on stuff for your headphones, right? So you can put little brain uh, sort of what are they called? It's gone out of my head at the moment. The receptors that can look at what's coming out of your brain, right? The electrical receptors, and
Yeah.
they're trying to figure out right now whether it is enough to be able to do something interesting with, right? Is it EEG, right? The receptors. So imagine doing that on the inside of your ear, just through an earbud or something. So I think there's a huge amount of stuff in terms of sensors and monitors, and we all know that there are chips that can create sort of shocks and things to stop epileptic seizures. I think there are already things that can stimulate your vagus nerve. So that I think that whole thing is coming. And also potentially, so I'm one of the ones who, has a little computer on my arm that's measuring things like my heart rate.
Mhm.
You could imagine that having a lot more sensors on it if these sensors are little and tiny and low power. So that could come too.
Okay. So thank you so much, Sunny. For the next question is, how will neuromorphic computing impact AI, and what risks come with the brain-like machine? So I think half of the question we have already addressed, but the what risk come with the brain-like machine? So he's Swayam is asking for the different uh, risk as well. I'll just, yeah. So I pose the question, how will neuromorphic computing impact AI, and what risks come with the brain-like machines? So we are talking about here, or we can address about the risk. Yeah, yes, Sunny, please.
So thanks. So we've talked about some of the benefits of AI, but they're only going to be benefits if we actually go at this field with purpose. If we as a society decide to impose that we're going to do good things with this technology and not any old thing with this technology, because we can all think of really terrible things that we could do with this technology, from surveillance, from artificial soldiers, from all sorts of horrendous things. So I think that's the one thing is, and no surprise from my point of view, this all comes down to regulation in the end. But there are also issues to do with plagiarism, and I'm not just talking about plagiarism like the stuff that I find on Turnitin with my students all the time. I'm talking about plagiarism as in you've got machines that look at the internet, and then you get a self-fulfilling prophecy where you're just recycling the same information all the time. We're having problems with this already in some of the models because they're just taking a whole load of rubbish that's out on the internet and recycling it, and it's wrong. A really good illustration of this is a very early neural network application that I saw. This is like 25 years ago. Was called 20Q, right? And it's a 20 questions game where you say, is it an animal, a vegetable, a mineral? You keep asking questions. And what was hilarious is if it asked you, is it a mammal? And you said no, it knows that enough people are so stupid that they would think that it could be a whale, even though that you had said it wasn't a mammal. So we just encode biases, misinformation, all sorts of rubbish into our AI. And if we continue to do that, then that's going to be a problem. The other thing I want to talk about is profit in politics. So it's all P's. So profit is the fact that if we're building technology to just enrich the 0.1% of the population, then it's not going to help anyone. And we have to look at how society is regulated. This is not something just for technologists. We've got jobs just like anyone else has got jobs. We're just wage slaves. But there are people at the top who are doing whatever they like and are operating like oligarchs. And they're not just in, the kind of countries that we normally associate oligarchs with. They're in the US, they're all over the world. And finally, politics. We know that AI of all flavors is being used to manipulate us as individuals, manipulate our politics, feed us misinformation. And yes, we can be vigilant as individuals, but again, we need society, we need governments to go in and regulate these people, not just take the fact that it can be if they've got the money, it can be advantageous to them to be able to have that manipulation available to them. Do you see what I mean? And I think a lot of times establishments will just let something that they know is bad, they'll let something run because at some stage it's had some advantage to them.
Yeah, any insight on this particular question? Inga?
No, I'm not really into brain-like machines, to be honest. But yeah, I absolutely share this perspective that we need to restrict the usage before we deploy neuromorphic computing in anything. So we have to protect the people by law, and we have to have maybe some kind of oversight committees to establish to maybe monitor and regulate the use of these systems also in surveillance. And the restrictions should limit the use of these systems to specific and justified scenarios where maybe where the national security is at actual risk, and to protect the people as well.
So that is what you have addressed the one of the questions, that what are the long-term societal impacts of widespread adoption of a neuromorphic systems, and how can these impacts be anticipated and managed? So that is our next question. So you have partially, if any say on this, Sunny?
I would say that the long-term societal impacts are of capitalism, not of AI. AI is just one tool, one thing that's being exploited by people who want to exploit most people, or that can be put in to the aid of most people. So I think it's the underlying societal regulation that's important. So
Correct.
to me, it's all about regulation um, uh, at uh, at some sort of sensible level, and people just staying on top of it, and also people staying smart and educated. You know, I mean, one of the things that I always find so impressive about India is that um, so many people, even who aren't working in the field of technology, know something about technology, you know, and feel that it's important to stay educated beyond just, you know, whereas when I was growing up, especially in the UK, it was considered that you know, technology was something that nerds did. It wasn't something to be interested in if you were cool or if you were cultured. And I think that we all need to know what's happening to change our society, and these are going to have impacts, but they could be good impacts if we work hard, if we don't let these companies just do whatever they want because they're bigger than the economy of single countries. You know, if we can hold them back and hold them to account, then it could be a good impact. But it won't happen by accident. They're not going. You know, it's not in their interest. They just want the money, and that's the problem. Is you have these corporations that are essentially psychopaths by design. I'm not even talking about the people who run them, or though some of them are psychopaths too. But the corporations themselves have no societal interest, right? Their only interest is in
Correct.
making money for their shareholders. And that to me is problematic, and that is something we need to fix. And I can't do that as a technologist or a lecturer. That has to be done by the whole of society.
Correct, correct, absolutely. So this is there is a widespread of the responsibility whenever the some companies are implementing these solutions or this type of technology. So societal impact needs to be taken care. That is known as the social responsibility, and that needs to be there with each and every organization and a company. So Vidhi, are you there, Vidhi? Okay. Great. Then I think there are so many and different insights we have got it from different panelists. They are insightful actually. The collaboration for working for the this particular technology, we need to have a collaboration with a different area because this will require the science, technology, the blend of these things. So we need to have a collaboration. That's a key point. Every panelist have pointed out on that. Then there are the repository wherein if you wanted to start this with this technology, uh, please do check as per Liana and Henga that even Sunny has also said there are already repositories available. So that is very important before starting with this type of computing technologies. So thank you so much. So this is a great talking and a great session and a great insights from each and everybody. So I would like to invite the host to get into jump into the things. Yeah, Aryan.
Thank you, ma'am. With such an esteemed panel, we are in for a thought provoking and inspiring discussion. Let us dive into the conversation and explore the exciting possibilities that lie ahead in the world of neuromorphic technology.
Thank you so much.
As we near the end of this enlightening discussion, I would like to extend a heartfelt thanks to present a token of gratitude to our exceptional moderator, Dr. you have any share, we would be delighted to hear them. Vijay ma'am,
Yeah.
if you have any final thoughts to share, we would be delighted to hear them.
Actually, it's not a problem. We have already summarized the session, and we are good to end the session.
Thank you, ma'am. Next, I would
Thank you.
like to
Thank you.
express our heartfelt gratitude and offer a token of appreciation to Mrs. Hanga Katrina. Your insights into neuromorphic computing have been incredibly enriching. Miss Katrina, we would love to hear your final insights.
Okay, I would like to thank you for the opportunity to be here today. It was a pleasure to me, and actually, I've never expected such an opportunity since I'm just starting on this field. So it was really nice to hear some insights from various backgrounds, from various people, and I really appreciate the opportunity. Thank you.
Thank you, ma'am. I would also like to convey our sincere gratitude and offer a token of appreciation to Sunny Baines. Your extensive knowledge and perspectives on neuromorphic engineering have been truly illuminating. We would also like to extend a sincere appreciation and token of gratitude to Lana Usa for her valuable contribution. Your contributions have given us valuable insights and a fresh perspective on future of neuromorphic technology. Lastly, we would like to give a heartfelt thank you and token of appreciation to Vidhi Vaghila. Your insight have greatly enriched our discussion. Mrs. Vidhi, your perspectives have been invaluable, and we appreciate the depth and breadth of knowledge you all have shared with us today. Let us give a big round of applause to all our speakers.
Thank you so much. Thank you. Thank you, team. Thank you, our IEEE SIA GST. And keep growing. Keep
Yes, ma'am.
growing.
Thank you, ma'am. Thank you
Yes,
for
ma'am. Sure.
all.
Thank you, ma'am.
Thank you for your engaging questions and for being such an active part of today's discussion. Your participation has made this session even more dynamic and impactful. As we conclude, remember that the journey from silicon to snaps is just beginning. The ideas and innovations we have explored today are just the tip of the iceberg. We hope you leave your feelings inspired and ready to contribute to the exciting future of neuromorphic computing. On the behalf of the entire SIS GST IEEE family, thank you for joining us for this incredible symposium. We have loved having you here and look forward to see the amazing advancements you will make in this field. Have a wonderful rest of the day and keep pushing the boundaries.
Thank you. Thank you so much.
We
Thank
also
you.
hope to see you all soon at our next exciting session under the MTTS track, where we will continue exploring the future of autonomous system and cutting edges technology. Until then, stay curious and keep innovating.
Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you very much.
Thank you very much.
Thank you so
Thank you
much.
very much.
Thank you.